I just assume that most of you have seen this planet. I have to control my screen. How do I stop this? I assume most of you have seen this a few times. This is a very good introduction to performance optimization in general, and especially when it comes to network and web. And there are some really interesting points here. For example, if you can avoid sending a packet across the Atlantic, it's worth it to do almost any amount of work on the server. From the client's standpoint, of course. Or more trivially, if you can avoid looking anywhere on the hard disk at all, it's worth it to look all over the main memory. I mean, you can make as much generic work in the main memory as you like, as long as you don't look at the hard disk. And you will save an enormous amount of work, or at least time. Even if you have to make a round trip within the same data center, you save a lot of time from making a disk click, which is the reason for memcache, for example. I have benchmarked this slightly on my own, or at least added a few points to it. Let's see if I can. The F1 here refers to an F1 type instance on App Engine, and that's like a 600 megahertz computer. So here we have some Go-specific benchmarks as well. For example, here, if you want to look in a native map in Go, it takes you about 350 nanoseconds. If you have a slice that you make a linear seek through, and in this benchmark, I didn't stop anywhere. I just compared each entry in a linear 100 element long slice to a generic integer. It's much faster. This is one really interesting lesson. A map is fast if you scale it. I mean, it will take about the same time if you have 1,000,000 entries as if you have 100 entries. But if you only have 100 entries, just stick with the slice, because this entire slice will probably be in the level 1 cache, or in worst case in the level 2 cache. So looking through it is almost instantaneous. We can also see that locking is, well, it's slightly more expensive in my Go example than in the number just taken from the original document. Maybe because the App Engine instance of type F1 is slower, maybe because Go has more overhead. But it's still quite fast. And it still doesn't make the native map that much slower. A year ago or something, I created an atomic lockless hash map in Go. But when I was finished and benchmarked it, comparing it to the native map with just a trivial lock around it, I noticed that I needed to have at least 4 or 6 CPU cores accessing the lockless atomic map at the same time to make it worthwhile. Because if you have fewer concurrent threads than 4 or 5 or 6, the native Go map with the lock around it is still faster. I can even show you the exact benchmarks. Here, the native map. This was Go 1.0, I think, not 1.1. So it's slightly slower, but it's 560 nanoseconds per read and write, 2 operations. And this my map is a native Go map with an RW mutex protecting it. So read operations don't collide, but write operations collide with everything. And just that lock in Go 1.0 made it a whole microsecond slower than the native map without the lock. Let's see, the native map. Here this mutex was only 100 nanoseconds. It might be optimized since then. But when I did it concurrently with 4 CPU cores, this was on my old MacBook Air, it's suddenly the lock competition made it take 10 microseconds instead of 1.5. And here is my, here's the concurrent hat map. If it wasn't concurrent, it took 5 microseconds, which is, I mean, if I only had one thread, it takes 5 microseconds just to insert and read. But if I run 4 threads concurrently, it's the same speed as a native Go map with a simple lock around it. So the lesson from this is that it really doesn't pay off to use atomic lockless data structures unless you have a whole lot of concurrency going on. It's sad because it was a whole lot of fun building the data structure. And a channel in Go is, as I may have talked about in an earlier meetup, it's actually quite a bit slower than a simple mutex lock-unlock. Maybe because the channel is a much more complex data structure. I haven't looked at the internals.
Is that the general number, like 300%?
Okay, about those numbers. I mean, this is just an example, and it all depends on what your machine does in the same time. But it's, I think we can assume that it's at least twice as slow as just a lock-unlock. On the other hand, it's not. I mean, it's not a microsecond. It's still quite fast. So I think that the thing to go for when you want to optimize is use the type of lock that fits your algorithm. If you want to lock communication between 2 concurrent processes, use a channel because they're really good at that. If you just want to lock a static data structure, the mutex does its job very well. Here is also an interesting point. This benchmark, if anyone is interested, the entire suite of benchmarks here can be found here. This is, I work at a company called Soundtracker Brand, and we are a subsidiary of Spotify, and we are building tools to play Spotify in commercial venues. Spotify in a shop or a cafe or a restaurant. And this package is our sort of extract tools that we use ourselves that aren't actually part of our product. It's just infrastructure that we both feel like anyone should be able to use and improve and find bugs in. But it's also, of course, a bit of PR and a bit of just goodwill. And here we have the bench package. And if we look for the reflective, here reflectable, what it does is I do a reflect value of a variable, find a method by name, I call it with a slice of reflect values, and convert the first return value to a boolean. So it does a lot of reflect calls. I mean, really simple reflect stuff, just comparing an interface to something reflectively or seeing if it has a method is probably much faster. So this is actually quite a lot of reflective work that takes still only a microsecond. And people often talk about how reflection is slow, don't use reflection. But I mean, if you compare to, for example, you have a database layer where you want to simplify your common API code so that you don't have to duplicate all your code for each different type that you store in the database. Okay, let's say that you need to read data from main memory, and you need to first you need to reference main memory, and then you need to read from memory. And if you have bad luck, which you often have, then you need to make a disk sync. I think we can conclude that a bit of reflection doesn't cost all that much. So I think that if it does does make an improvement in your code, use reflection. Don't be afraid of it.
Are there any specific like traps in reflection that one should look out for?
Reflection tends to panic. I can show you a bit of our util package. This one. This is app engine specific tools for example, wrapping data store reads in memcache and invalidating the memcache when you update or delete the data. And we have a whole lot, almost all functions in these packages have this huge row of sanity checks. For example, the model I send into this function, it has to be a pointer, so return an error if it doesn't. It's that to be a pointer to structure. It has to have a field called ID, and the ID field must have the type pointer to key.key. If all this works, I will accept and return. And this is sort of a sanity check used all over this package, because lots of these functions will just panic if I try to use them without these sanity checks. And that's another thing. Now I'm sort of straying into App Engine discussions anyway, but in Google App Engine, try to avoid panics, because your instance will die and App Engine will spin up a new instance. So unless you in your handler function defers a rescue of panics, then you will spin up a new instance every time you panic, which will kill your throughput. Of course, in a regular run-of-the-mill Go web server, a panic will just kill your entire server, and just to sort of survive serving any requests at all, you will probably either avoid panics or rescue them in the handler function.
But since we're speaking of performance, wouldn't it be more performant to defer and catch the panics and not having to do all of these ifs all the time?
Possibly, actually.
Because
I don't actually know how much time a panic, I mean, how much performance.
Yeah, but that shouldn't happen very often, right? Normally you would have a lot of, all of those ifs would never actually, normally they wouldn't happen. But now you're paying that price for every time you're using that code.
I think the ease of debugging may pay it off, because when I make a mistake and I see a nice error message instead of a panic, I may solve the problem quicker. But I think you're right, purely performance-wise, because it shouldn't be that often that I send the wrong type of interface into this function. On the other hand, this function will read from memcache in the same data center at the very least.
Yep.
It might even read from data store. And a data store get takes 6 milliseconds. So I think in this case it's marginal, but yeah, I think you have a point.
How is it? Does Go have asserts, and can you close them kind of when you compile?
How do you mean?
Like, so you could turn on and off the asserts when you run it to production.
You just write a normal if statement, and if you do it on a constant, which is known as compile time.
Yeah.
The compiler will
okay, so you have a Boolean constant, and the compiler will clean it away if it's a false.
Yeah.
Interesting. That's a really good hint. Okay, so other optimization tricks when it comes to Golang. For example, something you have probably all heard of, I don't know, the garbage collector. the garbage collector is slow, at least slower than you want to. So we have a slice. What's the problem here? Can someone point it out?
Shall they clean up the bin every loop?
Yeah, exactly.
Garbage.
This is theoretically faster, although this will probably generate the same amount of garbage anyway. So let's make it a slightly more realistic example. The difference of declaring B here and here can be really big if you have a tight loop that is used a lot in your program. A really trivial example.
What prevents the compiler from analyzing that?
I don't think anything prevents it, but I think the current Go compiler doesn't understand.
But it's a semantic of the language, right? That you really...
Yeah, I mean, there are lots of semantics. For example, if I...
But when we're talking about the garbage collector,
yeah,
what we really care about is if it goes on the heap or the stack, right? So
yeah,
we're not really afraid of putting a little integer on the stack every iteration of a loop. That doesn't matter for the garbage collector. What we care about is, do we create heap garbage? Right?
Yeah, but I mean, if it doesn't clean up the stack directly, I don't know. Maybe the
garbage collector
maybe this was still a bad example. Maybe this will actually be cleaned from the stack in each loop. I don't know.
Yeah, but it's not. It's only on the stack, so it doesn't matter for the garbage collector. A good example for the garbage collector is, for example, if we have a byte buffer.
Yeah.
If we create a byte buffer on every iteration of the loop, then we create garbage on the heap.
I think the same escape analysis is used for any type. I think the byte buffer.
Sure. But it's kind of, you would never create an int on the heap. Pretty much never. See, so
okay.
but while strings are always on the heap, right? And byte buffers would also, I guess, almost always be on the heap.
Do you really think the Go compiler cares about type?
Yeah, in this case, because you know the size of the type, right? An integer is always the same size, so you can always put it. And an array also it has a compile time size. But a string would, a string in itself is a length and a pointer to some kind of memory, but that memory will be created on the heap.
Yeah, a slice is also a fixed size, because I mean a slice has an array, a backing array, which is a fixed size type.
Yeah, but well, basically the slice header that is probably on the stack.
Yeah.
It's the backing data that is.
Do you know this for a fact, or is this a
well, the backing data is what normally would be very difficult for the compiler not to put on the heap.
Yeah.
So that's what you don't want to leak that to the heap every iteration of a loop if you can avoid it.
Yeah, that's true. But I mean, are you sure it would put it on the heap just because it's a slice?
It depends, I guess. But for example, sprintf will always leak.
Always?
Yeah, it always creates a string, right?
Yeah, of course.
And that string can't be on the stack because it needs to be returned from. It needs to be returned from the function to the caller of sprintf.
That's true. What I know of the escape analysis is that this will always allocate on the heap, of course.
In this case,
Maybe
well,
it would
I'm not sure.
maybe it would become a constant.
Yeah, he who could be a constant at compile time. So.
Okay. Now we should allocate on the heap, right?
Yeah.
Because the escape analysis would determine that this would be accessible outside the function. Do you know if it performs escape analysis on a for loop as well?
It probably does, but I'm not sure exactly what you mean there.
I mean, if I allocate memory within the for loop, will it be deallocated? I mean, if it puts the memory on the stack for each for loop, will it pop it again?
Well, if it's on the stack,
yeah.
it doesn't have anything to do with garbage collection, so then,
yeah, exactly.
then you're
yeah.
okay.
Yeah. And the escape analysis is used. You see, I'm not the perfect
The escape
speaker when it comes to
analysis is
Go
actually
optimization.
about, hey, can I not put this? Is it okay
Yeah.
to not put it on the heap?
Yeah.
That is what the escape analysis
Exactly.
is doing. So, okay, I can put it on the stack because the escape analysis has proven that this piece of memory, there's no pointer to it that escapes.
Yeah.
That's what the escape analysis is doing. So then it can not put it on the heap and put it on the stack instead.
Yeah.
So
That's a really good discussion. So basically, whatever you do within the function that doesn't leave the function should be on the stack. But you say that some types, like the bytes, yeah, of course, because it ends up on the heap. Yeah, of course, because sprintf will allocate on the heap within sprintf. Yeah, of course.
Yeah.
So what's the lesson here? What conclusion can we draw?
Yeah. Do you have any rule of thumbs that you could summarize?
Yeah, I thought the rule of thumb was really simple. Don't declare new variables within for loops or any tight loop really, which is basically only for loops. But maybe the rule of thumb isn't that simple anymore. Escape analysis didn't come into it when I thought about this earlier.
Yeah. For example, here
What would you suggest?
B is the small integer, right?
Yeah.
And even though it looks like you're creating a B on every loop of the iteration of
Just
the loop,
works on the stack.
that's actually not a problem at all, because B never escapes this function.
Yeah.
So, for example, if here you would take the address of B and give the pointer to each new B to somewhere
can
else,
you think of an example
then
that
that would be a
is
problem.
actually useful here then? I find myself stumped. I would like to create an example where I allocate memory.
For example, say we're using this scanner, bytes scanner, right? So you use it to read one line, every line from a file.
Yeah.
You can ask it for a string, or you can ask it for a byte, right? And if you ask it for a string, you will create a new garbage,
heap allocated memory.
A heap allocated string on every line that you're reading from your giant file, right? But if you ask for the bytes, it will actually just give you a pointer to the internal buffer in the scanner.
A slice, right?
So on the next iteration of the loop, it's still the same bytes buffer. So the internal byte buffer in the scanner will be over.
I have a question there because I was doing exactly this. What is the most efficient way to copy this? Because if you're doing in a concurrent way, then you need to copy it out. Otherwise, it might be overwritten again because it's just a buffer. So you need
to have another byte slice or byte buffer and just copy the bytes there, right?
Yeah,
and if you can, you can perhaps try to avoid creating new buffers yourself every line of the loop, if you can, right? So because maybe you only need to.
Does it matter? If you don't,
the backing memory of the byte slice will probably be difficult for the escape analysis to be able to put it on the string.
So if I do
because
like this,
if you're reading a file, you don't know how large each line will be.
But I mean, this byte here, would it be on the heap or on the stack? Does the escape analysis handle this?
I don't know. It could theoretically put it on the stack.
Yeah.
I agree.
So if the handy were a variable that you got from somewhere else, a second function. Let's say you didn't have it in the main, you had it in another function.
Yeah.
And you did that.
Yeah, then it would be on the heap, of course. Yeah.
But you wouldn't know.
But in this case, if I want to make it.
But the important thing is actually, if I just create one byte buffer on the heap, and I manage to reuse that when I'm reading my 1 million lines, then that's good.
Yeah, of course.
But if it's the case that you're creating 1 million byte buffers for all of your lines here that you want to avoid.
Yeah, of course. What I'm trying to figure out here is if this example that I have actually read about elsewhere is actually useful anymore since the escape analysis was introduced. Because maybe my competence here is moldy and no longer relevant since is it Go 1.1 or 1.2 that introduced escape analysis?
I'm not sure.
Oh, anyway.
But perhaps you shouldn't. You can't expect all the programmers to always know exactly how the internals of the compiler is working and how it's changing all the time.
Of course not.
So I really don't know exactly either what it will do with B. I think, but you can still have like. I think you can make a high-level argument about. It's reasonable that I make it easy for the compiler. I mean, I make one buffer and I know I'm reusing it.
Yeah.
You can see that.
Yeah,
that's
sort of my point as well.
Here, I know that it looks like it's very difficult for the compiler not to create new buffers all the time.
Yeah. So you sort of agree with me here. Okay, let's see there. Now I will just allocate a new one anyway. I'm trying to make an example that works. but what I understand from you now is that you agree with me that if I can allocate something outside the loop and reuse it, I should do that instead of allocating it within the loop.
Yeah, sure.
Yeah, because that was sort of the the salient point of my example, even if it became much more complicated and confusing before I reached the end of it.
Sorry.
Yeah.
But you still on the last line of the loop, you still invoke a string method. It still creates a string.
Oh yeah, that's true. Sorry. Let's do something different. This will of course also create a string.
No, this is good.
Are you sure?
Yeah, I'm pretty sure.
Okay.
Because the internal, the print will, yes, it knows that I should print this byte thing as a string. It doesn't need to create the one, I think.
Can I clear this? Yeah, I can reset it. So this then is much preferable to this.
Yeah.
Yeah, that was what I was trying to get to all the time. But I think this discussion was much more worth than the example.
Yeah. So, could you summarize a bit for us newbies? Like, is it because of it's in the loop and it does something strange, or is it just to?
I think the main point here is try to reduce memory.
Yeah, absolutely.
I mean, think about the big things like, oh, here's a big piece of memory that is needed for this buffer. Here's a big piece of memory that's needed for this string, and think about when does it seem like I'm creating this, right? And don't create a lot of these big expensive memory areas.
Absolutely.
Yeah. So let's see. What time is it? Yeah. Let's go to something a bit less theoretical and a bit more practical. Who here is familiar with memoizing? Okay, memoizing is, as far as I understand it, sort of generic term for the technique of trying to cache the results of expensive operations whenever you do them, so that the next time you do them, you can have a cache key and just fetch the result from the cache instead. It's often used in a pattern looking like this. In this case, I have a function called memwise. I send in a key string for the memcache key that I want to store anything under. And this is just Golang. I have a destination pointer where I want to store the results, and the generator function that returns what I would like to find from memcache if it wasn't there already. So basically, I will use it something like this. This is just very much pseudocode. And this is really useful if you have expensive SQL queries, for example. You have a huge join to find today's most popular blog entries, for example. And you want to join and sort and process your data a lot in SQL, and it takes 5 seconds to run the query. And you find 10 blog entries. And this only changes once a day, or maybe every time someone votes on the blog entry it can change. The point is that maybe it's fetched 100 times a second if you have a big site, and you don't want to spend 5 seconds generating the value each time. So you use memcache or just RAM memory, but if you want to have it scalable to a cluster, you are better off using memcache anyway. Then you can just use this pattern, which is really, really useful, because then you can, in a very simple way, just wrap your expensive functions in memwise, which will make them as free or as cheap as memcache call most of the times. Of course, as always with memcache, you need to invalidate the memcache properly. Perhaps in today's top blog entries, you want to have a timeout so that your memcache is invalidated automatically after 24 hours. Or maybe you have, like in our example here, the get by ID here always memwizes, because memcache access is 3 milliseconds, data store get is 6 milliseconds. And since we often get the same things a few times in a row, because people tend to go back and forth on lists and reload pages and so on, this tends to pay off. So I always memorize the actual finder. And in this same package we have sort of query functions as well that are much more expensive. At least often they are expensive. And we have, in other places in our application, we use memwise to find data and then find sort of decoration data, find the addresses of a user or the friends of a user. And that whole operation is quite expensive in the end. But with the memwise it becomes cheap. And the key I use here is, in this case, just created from the ID. But in other cases, when we have a query, I have keys that are much more sort of specific. For example, let's see where I generate keys. Here I generate a key that is based on the type of the data I'm looking for, the ancestor of it, which is basically what key resides under in the database, and then the field this finder is using, and the value. So for example, if I want to find all users with first name Martin, then I will first look under user, and then if an ancestor was provided, for example, users under Stockholm, then I would have ancestor Stockholm, and then first name Martin. And whenever I update or delete a user, I will do memcache invalidation of the type, the ancestor of the type or the data, and all the, and in this case Martin, first name Martin. And if I had registered several finders for this data type, I would invalidate a lot of things with memcache. And memcache invalidations are of course not free, but they are quite cheap, and you can do them asynchronously in bulk. So this pattern is quite useful in a lot of ways. You can even, if you play a bit dirty, you can even invalidate whole chunks of keys at the same time if you have a single level of indirection in your memcache. So this is really hard to explain. Perhaps if I start an editor. I want to memorize something under users, and then first name Martin, and then I have a func. And then, or even better, I want to memorize not something as simple as that, but a query. Like this. And then wherever I save a user, I need to invalidate all the query results from users, because I'm using, say I'm using Solar for searching, and I cache the Solar results in memcache with memwise. Then I need to, whenever I update a user, I need to invalidate all the search results, because I don't exactly know what Solar would return, or for what queries this Solar would return this user, or even what queries have been run. Maybe a million queries of different types have been run. So I want to just do a something like this, and then I want to invalidate all these queries, which are different, of course. This can be done quite simply. It will cost you an extra round trip to memcache. But what you do is you create a new memcache key from the key under users. So basically you fetch this, and if it was in memcache, say that you returned this number, then you do this. Then whenever you want to invalidate this, you just write a random number there. And suddenly, whenever someone wants to get the same set again, they will do memget. Like this. Which is not the same key. So in one mem set, you just invalidate everything that you stored, at least in your algorithm, under the key users.
So you look at group cache as well, because that's got the concept of groups which do the same thing, and that's the modern replacement for memcache.
Actually, I haven't even heard of it. That's really interesting. Do they have this built in, or is it a smarter model?
I know very little about it. I know it's got groups which do similar to what you're doing.
Does it cost twice as much to get them set?
No, I don't.
Because well, I implemented this. Oh, sorry. Memcache. Here. I just do an extra memcache before I fetch the actual key. So this is sort of an implementation of the idea I just explained. But you said group cache.
Yeah.
I haven't used it, but I think group cache is a bit different in that it doesn't allow you to change a key at all.
Oh,
So basically,
can you
all of
invalidate?
it, you could see it as everything in group cache uses your that invalidation technique.
Okay.
You have to use that. If you ever want to change anything, you have to include some kind of
Okay.
number.
What happens if you try to store something under the same key twice?
You can't change it. You need to you need to make up a new key name, I think.
Okay, so all keys have to be unique.
Yeah.
Interesting. I see. Well, I have to look this up. Yeah, as usual, the discussion is much more interesting than the speech. But that's good. Tell me, do you have questions?
I think the speech was really interesting as well. So.
Well, thank you. It was really badly prepared, but I had a busy day. You might even say it wasn't prepared at all.
Very valuable.
Sorry?
I think it's a very valuable kind of experience to kind of pointing out the important points.
Yeah.
For me as a new beginner as well, at least.
Please, is there anywhere you would like me to explain further, or any questions, or more errors to point out? Yeah?
I have a question that's completely unrelated.
Cool.
Just wondering, does GoFont format allow these long lines, or is it just your style?
Go format allows them.
Okay.
And if you try to sort of shorten them, it makes them ugly. if I add a new line here,
Yeah.
It becomes ugly. It doesn't handle it the pretty way I expect modern formatting tools to handle. So I tend to accept the long lines just to be able to use Go format. I would love a Go format that breaks this up and arranges it below the first C here, you know. But I think it would put all the other parameters here instead of under the C. Maybe you could add put a new line before the C, and you will get them in a column. But I think that's also ugly. So it's sort of like everything else in my experience in Go. It's sort of a compromise between the pragmatic approach of a lot of people, mainly the founders of the language. But in the end, it turns out very well. I agree that this line is a bit too long.
Perhaps if the line gets too long, though, you make a new type as a parameter type.
Yeah,
That's
yeah, of course. A parameter type is really nice. Yeah, this, for example, could be a type, and then I would cut lots of this. It's a bit of laziness here. Okay. Thank you for listening.